Hello everyone, I'm Marco Slot. I'm a principal software engineer at Microsoft, and I'm going to talk to you about our industry track paper, Citus Distributed PostgreSQL for Data-Intensive Applications. So this paper describes some of our experiences over the past 10 years building Citus, which is the first distributed database that is developed entirely using the PostgreSQL extension APIs. So it adds two features to PostgreSQL: distributed tables, reference tables. Newer versions also add columnar storage. And the goal of Citus is to give you the simplicity and flexibility of using PostgreSQL with its SQL support and indexes and transactions and all the capabilities it has at any scale. And that means building a multi-purpose database that can scale both transactional workloads by routing and delegating transactions across a cluster of PostgreSQL servers, as well as analytical operations by parallelizing them across the cluster. Now, over the years, we talked to a very large number of companies that were looking to scale PostgreSQL, and we noticed that their workloads at a high level mostly fit into 4 workload patterns. And the reason is that these are workload patterns for which PostgreSQL is commonly used, but they are also likely to run into scalability bottlenecks that can be resolved through scale-out. And for example, a common pattern we've seen very much is software as a service. So there are many companies building software as a service, and they can very easily add more customers, and therefore grow quickly. But that also creates scalability problems in the database because the working set is often very large. Now, of course, multi-tenant applications in general have the benefit that they can scale along the tenant dimension. I mean, a traditional approach has been to put every tenant into its own database or schema. But this does give you the burden of building your own distributed data management plane. And also for PostgreSQL, that approach doesn't actually scale very well. So with Citus, we can address this using distributed tables that are sharded by the tenant ID using a table sharing approach. Another common workload pattern is real-time analytics, and particularly analytical dashboards with a large number of users, which means they issue maybe hundreds of queries or thousands of queries per second on a very large data set that is continuously changing, continuously has new data being added to it. And so this is an area where traditional OLAP stores are not very suitable because maybe they don't really have the secondary index capabilities, or it's difficult to do roll-ups within the database. So PostgreSQL is quite suitable, but of course doesn't have the scalability characteristics needed to handle very large amounts of data. So that's another common workload pattern for scaling out PostgreSQL. Two other common workload patterns are the more traditional NoSQL use case, key value storage, for which PostgreSQL is also used quite often, in particular due to its sophisticated JSON support. So there's many options for querying JSON and indexing JSON. But if you start updating, you get a lot of write amplification, which then becomes a scalability bottleneck. And also the traditional OLAP workloads, where you have a large amount of data and a smaller number of analytical queries that scan a lot of that data at once. Now, what's interesting about these workload patterns is that each of them has a very different notion of what it means to scale. So for a data warehousing application, it's very important that you can scan very large amounts of data very quickly. Whereas for a multi-tenant OLTP application, that's not super important at all, but you do need to be able to support very complex data models involving many foreign keys and constraints, many tables being joined, and transactions involving many different tables. And those need to scale for the multi-tenant applications. So we need to build different types of scalability features into PostgreSQL, but also we need to be able to support the existing features in PostgreSQL. And also we need to support the features that are implicitly provided by the ecosystem in the form of extensions and tools. And so that is why we architected Citus as an extension rather than forking the PostgreSQL codebase, because PostgreSQL is a core project that has a new release every year that's packed with new features and performance improvements. But then there is also this vast ecosystem of tools and extensions that always converges to the latest Postgres versions and provides a lot of the capabilities around Postgres, such as the PostGIS extensions, which adds geospatial data types and operations. So an extension is basically a set of SQL objects like functions and tables to store metadata, and a shared library which implements the functions and can actually manipulate Postgres' behavior. So to create a Citus cluster, you just set up regular Postgres servers and install the Citus extension, and do create extension Citus to create the SQL objects. And we typically assign one node as the coordinator, which holds the authoritative metadata. That's the node through which the application connects. But the metadata is relatively static, so we can also synchronize that to all the other nodes or set up multiple coordinators. So Citus adds two new types of tables into PostgreSQL. So one is distributed tables, which are transparently sharded across the worker nodes. The shards are just regular PostgreSQL tables, which can have indexes, foreign keys, constraints, custom types. Distributed tables can be co-located with each other to enable foreign keys and joins locally on the worker. And then you have reference tables, which are replicated across all the nodes for fast joins and foreign keys. Now, once you've set up a distributed table, the goal of Citus is essentially to make it look like a regular table. And for that, it uses a number of hooks or extension APIs to hook into different parts of the Postgres code. We already saw user-defined functions like create distributed table, but one of the most powerful hooks is actually the planner hook, which allows you to replace the Postgres query planner from the top. You can also do that with the executor. And then there is a custom scan hook, which allows you to put custom nodes into a PostgreSQL execution plan. There are critical parts of the transaction lifecycle at which you can run custom code. There's a utility hook for dealing with DDL and copy and other commands. And then you can have background workers, which are extra background processes that are connected to the database so they can read from the catalogs and do transactions. So if a query comes to a coordinator node, what Citus would do is send queries in parallel to the worker nodes, just regular SQL queries that are planned separately on the worker nodes just by Postgres, and then aggregate the results and return the response to the client. And the way that integration works is via the planner hook. So after Postgres parses a query, it calls the planner function. And the only thing that does is it checks if the planner hook is set, and then if so, it calls the planner hook. And otherwise, it calls the standard Postgres planner. And that means that an extension, when it is loaded, it can set the planner hook to one of its own functions. And that means that every query that is parsed by Postgres goes through the extension. Now, that gives a lot of responsibility, but the responsible thing to do is check if the query contains any distributed tables or reference tables. If so, call the Citus planner. Otherwise, go back to the standard planner. And so the result of the planner hook should be a query plan that contains execution nodes. And in this case, we would have at the top probably a hash aggregate to do the group by. And under that, we could have a custom scan, which is an execution node that just calls C functions to get tuples. And so in this case, it would call a Citus component called the adaptive executor, which parallelizes the query across the worker nodes using multiple connections per worker node. And then those tuples flow back into the Citus executor, the Postgres executor. Now, because we needed to support different workload patterns, one thing that happened over time in Citus is that we actually ended up with different layers in the distributed query planner. So for queries on a distributed table that have a distribution column filter, they typically just go to one shard, so we can recognize and process those queries with very minimal overhead to handle high throughput, basically high performance CRUD operations. Now for multi-tenant applications, we often have much more complex data models. And so for that case, what the planner does is it mostly looks for filters on distribution columns and whether those filters transitively apply via joins. If so, then it can, without further analysis, take the whole query and send it to the right worker node, because the worker node is just a PostgreSQL server, so it knows how to do joins and subqueries and window functions, etc. Now, if the query doesn't have a distribution column filter, it will need to be parallelized across the shards, but there are also some layers. In particular, if the query if all the distributed tables in the query are joined by their distribution column, big parts of the query can typically be pushed down to the workers without further processing. Of course, if the joins are not on the distribution column, then the planner needs to decide what is the best join order, how to reshuffle the data across the cluster. So that involves more overhead, but that's acceptable because the types of applications that issue those queries are usually reporting applications where the execution time expectation is relatively high and the number of concurrent queries is relatively low. So the different planners in Citus roughly reflect the different workload patterns for which we designed it. Now, apart from SQL and query planning, another thing we need to deal with is distributed transactions. Now, for simple transactions, we basically delegate the decision to a worker node. And that means, for example, for a multi-tenant application, which has where all those statements go to the same worker node, you basically get the exact same semantics as you do in PostgreSQL in terms of MVCC, and but then in a way that scales because we route the transactions across the worker nodes. Now, if your transaction spans across multiple worker nodes, we need to do a two-phase commit. And so we use for that the transaction callbacks. So there's a pre-commit callback where we send prepare transaction to all the worker nodes. This is infrastructure that PostgreSQL already provides in order to do two-phase commits. And then in the post-commit, in the pre-commit, we also write a record to a commit log. And then in post-commit, we send the commit prepared to the workers nodes. Now, if something fails in the first phase, we can just roll back. If something fails in the second phase or a rollback fails, then we have a pending prepared transaction on that worker node. And the way we resolve that is by using the background worker infrastructure. So we have a background worker that continuously polls the workers for their prepared transactions and then looks at the local table containing the commit records written by the coordinator. So if those records become visible, it means the coordinator decided to commit, and therefore the prepared transactions have to be rolled forward. If they're absent, then they need to be rolled back. And that's how the 2PC recovery works, and we provide atomicity. In addition to 2PC recovery, the background worker also does distributed deadlock detection. Because the Postgres protocol is interactive, it's very trivial to construct a scenario where you have two transactions waiting for each other, and that can be on different worker nodes. And to handle that, the background worker continuously polls all the workers for their lock graphs and then constructs a distributed transaction lock graph. And if there's a cycle in the lock graph, it cancels one of the transactions by just sending a signal to the process on the coordinator node. Now, we don't support distributed snapshot isolation because A, there's not really a hook for that in Postgres. B, in these workload patterns, we've also not seen a strong need or heard a strong need from customers. Because, for example, multi-tenant applications, well, they're complex transactional applications, but they always scope their transactions to a single node by using collocations or reference tables. And something like a data warehouse application doesn't really have many concurrent transactions going on, so it's also less important. But we may still implement this in the future, but it will require some changes to Postgres. Now, we also did some benchmarking to kind of demonstrate the scalability in each of these workload patterns. So, for example, for multi-tenant bench workloads, we used HammerDB tproxy, which is based on TPCC, where every warehouse is essentially a separate tenant. But some transactions do span across tenants. So we don't get quite linear scalability when going from 4 to 8 worker nodes, but pretty close. And then we also compared each of these workloads to a regular PostgreSQL server. So all the servers have 16 cores. And so if we have no workers, so essentially we're just sharding locally on the same server, We don't see a lot of benefit for transactional workloads. There's just some overhead, so typically throughput is lower. But for analytical queries, we do still get parallelism locally, and that can be very beneficial. And then with 4 worker nodes and 8 worker nodes, the data fits into memory, and we can see like how that scales. For example, with YCSB, we can see linear scalability. And with larger analytical queries, we can often see more than linear scalability because of more data fitting in memory. So this was the presentation. If you have any questions, you feel free to send me an email. You can also find more about Citus on GitHub, the Citus Slack, or the documentation. If you are interested in building a PostgreSQL extension yourself, well, Postgres itself has very good documentation, but also there's this GitHub repository that documents all the hooks that Postgres offers. So that can be a good place to consult. Thank you very much, and I hope you enjoy the paper.